Welcome to this video on human anatomy, biomechanics, and anthropometrics within the scope of ergonomics and occupational psychology. We will cover occupational diseases related to ergonomic factors, focusing on the basics of anatomy, biomechanics, and anthropometrics. Human anatomy is the scientific study of the morphology of the adult human. It is subdivided into gross anatomy and microscopic anatomy. Gross anatomy examines structures visible without aid. The musculoskeletal system enables movement using muscular and skeletal systems. It provides forms, support, stability, and movement to the body. The human body has 324 muscles, which make up 30 to 47% of body mass. The three types of muscles are skeletal or striated, smooth, and cardiac muscle. This diagram illustrates the structure of skeletal muscle, showing the relationship between the muscle fiber, endomysium, paramysium, and tendon. This detailed view of a muscle fiber highlights key components like myofibrils, sarcoplasmic reticulum, and the sarcolemma. A motor unit consists of a single motor neuron and all the muscle fibers it innervates. This unit is crucial for muscle contraction. Here we see the connection between the spinal cord, motor neuron, and the muscle, illustrating how motor units are integrated into the nervous system. This image shows a closer look at the motor nerve branching out and connecting to muscle fibers through motor end plates. The skeletal system includes bones, joints, cartilages, ligaments, and tendons. Bones provide support, protection, movement, and are essential for blood cell formation. Bones are classified into four main shapes: long, short, flat, and irregular. Examples include the humerus for long bones and vertebrae for irregular bones. Biomechanics, derived from the Greek words bios, meaning life, and mechanic, meaning mechanics, is the study of the movement of living things using the science of mechanics. Biomechanics is the scientific study of the mechanical principles of living organisms, focusing on how biological systems move, function, and respond to forces. Biomechanics is a large field combining physics, calculus, anatomy, and physiology to study human movement. It analyzes internal and external forces acting on the human body. Biomechanics bridges biology and mechanics to explain how living systems interact with forces, optimizing performance in sports, medicine, rehabilitation, ergonomics, and engineering. Kinesiology is the scholarly study of human movement, encompassing fields like anatomy, physiology, and mechanics. Biomechanics is one of the academic subdisciplines of kinesiology. Biomechanics and kinesiology precisely describes human movement and its causes. It helps enhance human performance through technique improvement and better equipment design. Applications of biomechanics include exercise and sport, orthopedics, occupational settings, ergonomics and engineering, focusing on injury prevention and movement safety. Orthopedic biomechanics focuses on artificial limbs, joints, and orthoses to improve functional movement capacity and studies natural and artificial biological tissues. Exercise in sport biomechanics improves athletic performance and reduces injuries by analyzing movement mechanics, such as a golfer's swing or a basketball shot. Occupational biomechanics studies the physical interaction of workers with tools and materials to enhance performance and minimize the risk of musculoskeletal injury. In the workplace, occupational biomechanics uses ergonomics and human factors to reduce workplace injuries, for example, by optimizing lifting techniques and seating posture. Comparative biomechanics applies mechanical principles to non-human biological systems, such as studying swimming in fish, locomotion in apes, and racing performance in horses and dogs. All applications of biomechanics share the common thread of applying fundamental mechanical principles to study the structure and function of living systems, using common analysis tools. Studying biomechanics helps answer crucial questions from a mechanical perspective. These questions include how we generate and control movements, and how to make our movements better. Biomechanics significantly contributes to industrial design by developing tools like vacuum grippers for surgeons and improving the design of ergonomic office chairs. Biomechanics improves performance from both the equipment and user points of view, applying mechanical principles to analyze human movement, as seen in the golf swing analysis here. Fixing problem jobs reduces musculoskeletal disorders and injury costs. Understanding human movement facilitates better teaching, coaching, therapy, and new research ideas. Biomechanics combines physics, engineering, anatomy, and physiology. This video will explore the biomechanics of skeletal muscle, including its principal characteristics, structural organization, fast versus slow twitch motor units, muscle rolls, types of contraction, and factors affecting force production. Skeletal muscle has 4 principal characteristics: contractility, the ability to contract and produce force; extensibility, the ability to stretch without tissue damage; excitability, the ability to respond to a stimulus; and elasticity, the ability to return to its original shape. Muscle contraction can be studied as a twitch, where active muscle force is proportional to the number of active actin-myosin binding sites. The number of sites depends on the muscle's length. Muscles assume different roles. The agonist causes movement, the antagonist slows or stops movement, the stabilizer stabilizes a body part, the neutralizer eliminates unwanted actions, and the synergist performs the same action as another muscle. There are 3 types of muscle contraction: concentric, where the muscle shortens; static or isometric, where there is no change in length; and eccentric, where the muscle lengthens. Cross-sectional area is one factor affecting force production. Hypertrophy, an increase in myofibrils and myofilaments, contributes to increased force. Hyperplasia, a debated increase in fiber number, might also be a factor. The force-velocity relationship states that force is inversely related to shortening velocity. When resistance is negligible, the muscle contracts with maximal velocity, resulting in low resistance and high contraction velocity. As the load increases, concentric contraction velocity slows down to 0 at the isometric maximum. This shows the inverse relationship between force and the speed of muscle shortening. In the workplace, working postures influence lower back strain. Both mobile and sedentary jobs pose injury risks. Frequent bending, twisting, lifting, pulling, and pushing are common risk factors for back injuries. For optimal sitting posture, avoid slouching, use higher seating to decrease spinal compression, and keep your back near a 90-degree angle to your thighs. Short breaks to move are recommended to reduce muscle fatigue. For proper typing, place the keyboard to keep wrists neutral. Position the monitor slightly below eye level and 1 arm's length away to avoid neck strain. Relax your grip on the mouse and use a document holder if needed. For general lifting, reduce the object's weight as lift frequency, distance, and size increase. Maintain a neutral spine. Lift with your lower body at a controlled speed and keep the load close to your pelvis. Avoid leaning or twisting. Potential areas influencing injury risk during lifting include the lifter's condition and technique, the load's characteristics, the task's demands, and the surrounding environmental conditions. Factors influencing lifting risk include the lifter's attributes, such as strength, endurance, and technique, the load's characteristics like weight and size, the task's complexity and frequency, and the workplace conditions. The biomechanical model of joint motion illustrates that external torque and the desired motion determine the internal torque required for movement or maintaining equilibrium. The external torque is determined by factors such as the magnitude and position of the load, the upper body mass, the position of the upper body, and inertia during the lift. For equilibrium, the internal torque must equal the external torque. If the external torque is 84 foot-pounds, the required internal torque is also 84 foot-pounds. To calculate the required muscle force, we use the internal torque formula. Internal torque equals muscle moment arm times muscle force. We need to determine the force needed from the extensor muscles. Given an internal torque of 84 foot-pounds and a muscle moment arm of 0.15 feet, the calculated muscle force is 560 pounds. This force is necessary for equilibrium. In addition to torque and force, joint compression is influenced by the speed of the lift and any rotation occurring in the transverse plane, which can increase stress. To decrease low back stress during lifting, one possible action is to reduce the weight of the load being lifted. Another way to decrease low back stress is to change the position of the load, bringing it closer to the body to reduce the external moment arm. The third method to decrease low back stress is to change the position of the body, which minimizes the distance the load is carried from the body's center of gravity. Comparing the 2 scenarios, the good technique minimizes the horizontal distance of the load from the center of gravity, resulting in less required torque compared to the bad technique. By applying biomechanical principles to lifting, we can improve technique and reduce the risk of injury. Anthropometry is the study of the human body and its movement. It involves collecting measurements, known as anthropometric data, often used in design for most population ranges. The term anthropometry comes from Greek, anthropos meaning human, and metron meaning measure. It assesses individual variations like height, weight, and organ size using instruments like 3D body scanners and neuroimaging. Anthropometric measurements, such as orbital height, sitting height, and seat depth, are vital for ergonomic design, especially for seated work environments. Applied anthropometry in ergonomics is the practical use of human body measurements to design tools, workspaces, and environments. This ensures designs accommodate human variability, enhancing safety and efficiency.